Morning. Thanks for coming today, this early Friday morning. Some housekeeping stuff. So next Wednesday, I'm not gonna be here. Oh, I know, it's sad. Everybody don't cry at once. But what we will do is I will record a lecture and post it online for you all to watch. You're gonna be responsible for that material, so that way we won't miss any time. We'll get caught up on Friday. And then the TA will use next Wednesday to A, pass back the midterms, and then B, hold a discussion section. So you can feel free to ask him for midterm questions, midterm clarifications, any other kind of things. Project 3, it's kind of an open discussion forum for whatever you want to do. So I will remind you before Wednesday, because I know that's probably necessary. So it should be a good opportunity for you to take advantage of having the TA then. Any other questions? Yeah?
Will the lecture be played in class as well, or should we do, does it have to be watched outside of class, or will it also be played in class?
No, it's going to be 50 minutes. It's going to be like a normal lecture.
Okay.
Yeah, so you'll be responsible for that content.
I thought you said on Wednesday that the TA was going to be passing out the midterms.
Yes.
At the same class time, right?
Yes.
So will the lecture be played in the same class time?
No.
Okay, this one.
No. So the physical class time period, right, is to hand back the midterm and to give you a discussion section with the TA so you can cover anything you have questions about, midterms, content, Project 3, especially Project 3. That's the time, a good time to ask him and ask all of you. But yeah, so we don't miss any content. There'll be videos to watch and content to keep up to date with. Cool. Any other questions before we get started? All right. Nobody wants to ask how the midterms were?
If you have that information.
I'd go up.
How were the midterms?
They're halfway graded. They were good. I was very impressed. With what I saw. The DNS one was hard to grade. There's a lot of different ways to write it, I've found. But that was good. I think it's a good learning experience. So yeah, all right. Okay, so let's go back to, we have been talking about the write a recursive descent parser, a predictive recursive descent parser, based on the first and follow sets, right? So we want this parser to be predictive. What does it mean for it to be predictive? Yeah.
Can determine how to parse based upon the first and follow sets.
Almost. Yes,
Sort of.
but what does it look to determine? It uses first and follow sets, but what about the input does it use to determine which rule?
Just one character?
Just one token or character, yes. Exactly. So yeah, the predictive part means by looking ahead, it can decide which rule by using the first and follow sets, right? And so we saw how to prove that, hey, this grammar does support a predictive recursive descent parser. Okay, so we've been looking at email addresses, and we've seen, okay, this is how we can define an email address. And we saw, okay, we already have the first and follow sets. We've calculated that. You can go follow this and to see how to do this. And so we can say, okay, then we can create a function to parse an address, right, this non-terminal. So to parse an address, we know that address is either composed of a name address or an address specification. So how can we tell which one? Is it a name address or an address specification?
First sets.
What first sets? Yeah, so but how do we decide? So that's how we can prove that we can decide, but how do we actually make that decision?
Just put the characters in one or the other.
Yeah, so what's the first thing you gotta do?
First set.
Before that, yeah.
You get the token.
Yeah, we first have to get the token, right? We have to read something in from the input, otherwise we have nothing to compare it against. And then we check the first of one of the rules and say, okay, is this token in that first set? Right, so we hard code this, and we say, okay, if it's, so here we can see name address is either a less than symbol, an atom, or a quoted string, and so we're checking, hey, if this t type is a less than symbol, or an atom, or a quoted string, then we know it's got to be this rule, name goes to name address. Why do we do this unget token here? What was it? The input is consumed. Why is that bad?
Because if you're going to one of the things and you have to look at that same token for one of the non-terminals that it goes to, then you still have to look at that.
Right. So yeah. So if you think about the tree, right? The part of the tree. Once we see this, we know. Okay, we have a tree where we started address, right? We're trying to parse address. We have an address node, and we've decided that okay, address has a child name address. Because of this rule, I know this rule applies, but name address is not a terminal, right? Name address itself is going to have its own subtree structure and going to generate terminals. So we had to look one ahead to decide which rule to choose. But if by looking one ahead, we moved the input tokens forward, right? But address itself, none of address's children are terminals. So we know that terminal has to come from name address and not from address, or from one of name address's children. We don't know. All we know is that address does not have it. And then we're going to call parse name address, right? So we have this recursive call that's going to call some other function that knows how to parse a name address. And then I'm going to say, okay, I chose the rule here. Address goes to name address, right? I know if I get back from here, what do I know? What do I know if I get back? If this parse name address call returns.
You're done. It's already parsed everything.
Yeah, it's parsed everything, and it's parsed it correctly, right? There were no syntax errors, right? So syntax errors stop the parsing and say, hey, there's an error, right? So we know if we've gotten here, we know that, okay, great, we parsed the name address successfully, and now we can do whatever we want. We can build this tree with this name address, this address and this name address node. We could do some kind of parsing, whatever we want to do. Yeah.
Is it bad practice to pass t-type into parse name address instead of calling unget token and then having parse name address called get token in it?
Bad practice. I'd say yes, because you're changing the semantics of these parse functions. Right? We're kind of looking at these parse underscore non-terminal functions as they take in no input, but they use the lexer to get tokens. Right, so if you have to then, for some of them, pass some input and for some not, then you're creating kind of this, you're muddling the abstraction, right? They're not all the same. But it's a way you could do it, yeah. Okay, then we need to check the first of address specification. So what are we going to check? Yeah.
It's the same process as before. We just use the first set and check against that.
Yeah, so we use the first set of the entire right-hand side, DAA, QSA. Right, and then what do? Do I want to keep this token or not?
Nope. Unget it.
Nope. Right, we want to unget this token. And then what function am I going to call? Let's go somebody else.
The address spec.
Yeah, parse address specification, right? So we know that's the rule. We know we have to parse it. If that returns, we know everything went successfully, so we properly parsed it. So what happens if it's neither of these two cases?
Throw an error.
Throw an error? Yeah, right? That means there's an error. And this is what the first set tells us, right? The first set of address says, hey, when we are trying to parse an address, if we read a token that's not in the first set of address, then we have a huge problem, right? Or we don't have a huge problem, we have a syntax error. This is not a valid string that came from this grammar because address can only start with dotted atom at, a quoted string at, a less than symbol an atom, or a quoted string. So we get a syntax error.
Are we going to have to account for that for any of the test cases? Like syntax errors? Or are we going to...
In this project, no.
Okay.
In this project, you just need to, you can assume that, in project 3, you can assume that it's well typed, but in other projects, that's not going to be necessarily the case.
So if we're receiving syntax errors, it's because the program that we have written is reading incorrectly rather than the test case is incorrect.
Say that again?
If we are getting syntax errors, it means that we have written something incorrectly in our project rather than the test case is incorrect.
Yes. A unless you wrote your own test case and your test case
From
is
the
wrong.
test case is given.
Yes, yes. Okay, so we can do this exact same process with name address. So we have the first and follows here. So this follows the same process. So what are we going to check first?
Display name.
Display name, yeah, it's the first of display name angle address, which is Adam quoted string. So we're first going to get a token, we check that, and we say, okay, so why am I doing display name angle address here, not just display name?
Display name has Epsilon, and you need to check both.
Yeah, right, so I have to check the first of this entire rule, right? Because if display name has an epsilon in it, then we say, okay, but we have to also take the first of angle address, right? And we know how to take the first of a sequence of tokens, right? That's what we do all the time. But because there is no epsilon in display name, right, it's just Adam quoted string. Right, so we check if t type is Adam or t type is quoted string. Are we going to do unget token or not? Unget. Yeah, we want to unget that token. We want to call parse display name. And then are we done? Is this the rule properly done?
No. We also have to parse the angle
Hesitant
address.
no. Why?
We also have to parse the angle address. We haven't handled that.
Right, so we've only created one child, right? We called this parse. So we have our name address, right? And we just parsed a display name, which is great. But now we need to parse. We know that after display name comes an angle address, right? And this is because of this rule here. Name address goes to display name angle address. And now are we done? Now do we know that is this rule good? If this thing returns? Yeah, right. If this returns, that means it was able to parse its own tree. Everything's syntactically valid there. So we can say, okay, I knew I chose this rule. So then what's the first set? We're going to have to check the next. So if it's not an Adam or a quoted string.
Check if it's a left angle bracket.
Yeah, check if it's a less than symbol or left angle bracket, right? So if it's in the first of angle address, we're going to call unget token again. We're going to call parse angle address, and we're going to say, hey, this was name address goes to angle address, right? So even though I have parsing angle address in both of these two if clauses, what's the difference here?
The top one has display name before the angle address.
Yeah. So the top one has a display name before the angle address, and I can tell which one just by looking at that one token, right? I know if it's a less than symbol, then it can only possibly have come from this rule. Whereas if it's a quoted string or an Adam, then I know it had to have come from this rule. It has to be a display name first, followed by an angle address. What do I do if it's neither of these?
Syntax error.
Syntax, our old friend, syntax error. Okay, let's, we're gonna go through this quickly because this is very same. We do the same process. This has only one, so we check the first sets and then we make sure it's in that first set, otherwise it's a syntax error. Okay, so here we have an epsilon. So here's what becomes interesting, right? So display name list is either a word followed by a display name list or epsilon. Right, so we want to do this parsing. What's the very first thing we do? We got it? Automatic? Yes, get token, right? We always get the token. All right, then what are we checking the first of? Word display name list, right? So we want to make sure we always check the entire rule, and then we see, okay, there's no epsilon in Word, so it's Adam quoted string. Right, so we check, okay, if it's an Adam or it's a quoted string, then we call unget token, right? And we're going to parse, what are we going to parse first?
Word.
A word, and then
Display name.
display name list, which is the same function, right? It's going to happen again. And then we're going to print out, hey, we parsed display name list goes to word display name list. So what do we do? If it's not this, do we just say it's a syntax error?
No.
so then what do we check? What rule are we trying to check, right? So these comments here, right, above this check is trying to convey what we're attempting to check, right? Yeah.
For the next condition, we check if the next token is in the, or if this token that we just got is in the follow set of word display name list because of the epsilon. So that's how we implement it.
Why word display name list?
Well, just display name list because there's no epsilon in words.
Yeah, because that's us, right? So yeah, so this is, we are parsing display name list, right? If it goes to epsilon, then that token must have come, it must be one of the tokens in our follow set, right? So it must be either an atom, a quoted string, or a left angle bracket, right? So we can't check for epsilon. When we call get token, we never are going to get an epsilon. Yeah.
Don't you mean just an angle bracket? Because we're looking at just the file set for display name.
Oh, yes, sorry. I was looking at follow word.
Yeah.
I didn't see that. Okay, yes. Display name list, left angle bracket. Yeah, so we check. Is the T type, is the token that we just got, is it a left angle bracket? If it is, then what do we do?
Return, wouldn't you?
If we just return, what would happen to somebody who...
Unget token return.
Yeah. Right, so we want to unget token, right, because we have to make sure, because we just read that token and we just proved it actually came from after us, not from display name list, right? So we need to make sure we push that token back so that we're not consuming that input. Okay, and then we print out, we say, okay, we got display name list went to epsilon here, right? So you can see this is a recursive call that's going to keep going until, as long as it's reading in essentially words, which are atoms or quoted strings, it's going to keep calling this until it reads a less than symbol. And then it's going to stop this parse display name list. The lowest one is going to return, and then we're going to actually have parsed that whole list. And it's going to create that tree structure for us. And what if it's not one of these? Yeah, syntax error, right? We know it has to be either in one of these first sets, or if there's an epsilon, it's going to be in our follow set. Okay, now let's look at, I believe, yeah, there we go, this is a good one. So angle address is a left bracket, an address specification, and a right bracket. Here's the first and the follows. So we want to parse this, first thing we do?
Get token.
Get token, they said all together. All right, so what do we want to check the first of? Yeah.
You just make sure that it's a less than symbol because it's what you're.
But what do we want to check the first set of if we want to not think about it?
Address angle, right? Or
Okay, yes, true. But our process is we want to check each of the rules, and we want to check the first set of the entire rule, right? So we want to check the first set of left bracket, address specification, right bracket to know that it's this rule. If there's only one case, yes, that first set is going to be the same thing as the first set of angle address. But just to show that this isn't a special case of the other properties. Okay, so we check this. What's the first set of this sequence?
left angle bracket.
Yeah, left angle bracket. So we say, okay, if the T type is left angle bracket, do we call unget token?
No.
Do we not call it? Do we want to call it?
Because it's a terminal.
Because it's a terminal? What do you think?
I think
What does everybody else think?
call it.
You should call it? What am I trying to parse here? What am I trying to make a tree out of?
The address.
So what's the root of this tree?
Angle address.
Angle address, right? And so what's the leftmost child going to be?
That left angle
The
bracket.
bracket.
The left angle bracket, which is a terminal or non-terminal. Is it going to have any children?
It's a terminal.
No, it's a terminal. And then what's the next child going to be?
The address spec.
The address specification, and the next child,
The other
right
bracket.
angle bracket.
the right angle bracket, right? So then do I want to call unget token?
No.
No, because address specification right? It doesn't care about that left angle bracket. That left angle bracket came from the angle address, right? It's one of our children. So when we call parse address specification, we need to make sure that we've consumed and moved that input and said, yes, okay, we've matched up correctly. We know that we generated a left angle bracket, which means when you start parsing, you should parse after that left angle bracket. So now that I call this, am I done? Do I know that now everything's all good?
No.
What do I need to do?
Then once that's done, then you need to check if there is a right angle bracket afterwards.
How do I check if there's a right angle bracket afterwards?
Get to it.
Yeah. So I want to, why do I want to get another token? We haven't done this before.
Because after you've parsed out address specification, your Lexer is looking right after that, but it hasn't gone on to the next character.
Yeah, so we want to know, right? We're trying to build these children, right? And say, okay, could this input string have possibly come from an angle address? So we know if the first case is it has to be a left bracket, right? And then we have to parse an address specification, which does something else that we don't care about. And then we have to make sure that we have a right angle bracket, otherwise it doesn't conform to this rule, right? So what if the type there is not a right angle bracket? Syntax error, right? It's a syntax error, it's a problem. And now do I know that I parsed this correctly and I parsed this whole rule?
Yep.
Yeah, so I can say, okay, this was my rule, left bracket, angle specification, right bracket. What if it's not in any of there?
Another syntax error.
Syntax error, yes. Okay. So we can see a similar thing here. We'll go over fairly quickly because there's other things we want to get to. So we follow the same process. We're going to parse the token. We're going to check if it's in the first of domain atom at domain. And do we call unget token here?
Excuse me.
Hearing a mumble of yeses and nos. Anyone want to venture a thought? Yes?
I'm going with no.
You're going with no. Who's going with yes?
Is DAA the terminal?
DAA is a terminal.
Oh, if it's a terminal then.
Right. Yeah, this is a terminal, right? So this is a token, so we want, all right, so they're all tokens, but this is a terminal, so we need to say that yes, this generated a terminal. We don't want to push that token back, right? We want to move the lexing forward and the parsing forward. And then we're going to call parse domain, and then we're good. And then we check the first of quoted string at domain. Are we going to call unget token? No, right? For the same reasons. And then we're going to output that. Otherwise, we say syntax error. Let's see. Okay, this is a pretty simple one. We just have domain is dotted at, or dotted atom is what the DA stands for. Otherwise it gets too complicated if the long names are here. Okay, get the T token, get the T type. What are we checking?
If it's in the first set.
Yeah, if it's in the first set of DA, so what's that checking for?
DA, the T type equals DA.
Yeah, T type equals DA, right? And then do we unget token? Do we call any other recursive parsing functions?
It's a non-terminal.
Exactly. We're at a leaf now, right? We're at a leaf, and we know we've read this domain atom, or dotted atom, right? So we say, okay, this is that rule. Great. And so we know there's nothing more we can do here. So we know whenever we get to domain, right, we're going to stop, and our parsing is going to continue. But we stopped, but we've consumed a token from the input stream, from our tokenizer, or from our lexer, right? So if it's not a dotted atom, error. Okay. A word is an atom or a quoted string, so this should follow pretty straightforwardly. We get a token. We first check if it's an atom, then I say great, word goes to atom. Otherwise, if it's a quoted string, I say great, its word goes to quoted string. Otherwise, it's a syntax error. Questions on parsing? How to write this parser? So because there's no questions, you'd be totally good if I put this on a midterm of here's a grammar, here's first and follow sets, write a recursive parser for this grammar. I'm supposed to encourage people to ask questions. There will be questions like that on the midterms and finals. This is important. There'll also be homework questions. Cool. All right. We're good. So we can actually turn this into rules about how to do this. So we can say that, I didn't roll this out. We can say, okay, to write this, there's actually a pretty straightforward algorithm that we've been following, right, while doing this. Right? We've been trying to reason about it and trying to, think about it, why this is correct. But we basically are going to create, for every non-terminal in our grammar, we're going to create a function called parse, that name of that non-terminal. Why don't we create functions to parse terminals?
Because there's not a point to it.
Right.
Yeah, right? I mean, non-terminals are going to generate terminals, right? So we don't have to worry about that there. So for each, when we're writing our parse A function, if we have a rule A goes to alpha, where remember we've been using alpha as a sequence of tokens of terminals and non-terminals, we check if get token is in the first of alpha, right, which is that rule, then choose the production rule A goes to alpha, right? So that's what all of those if checks we were doing, right? We were checking the first set of that entire rule. So that's why I tried to make a point about not just checking the first set of the left bracket, but you have to check the first set of that entire rule. And we're going to say for every terminal and non-terminal A in alpha, so we're going to go through, iterate through all of those symbols. If it's a non-terminal, we call parse A. If A is a terminal, we check that get token is equal to that thing that we're expecting, right? And then we have this rule which we have devised, right, of how to check if epsilon is in the first set of alpha, right? Then we know that to check this, we have to check the follow set of A. And basically this last clause just says, hey, if none of these cases happen, right, if none of the rules match, then we have a syntax error. Questions? Confusions?
I guess, like a general question, I'm wondering why we have been checking the type of the token and not like the actual value of the token the whole time. Against
What's the difference between the type of the token and the value of the token?
the type.
So let's take it back to what are tokens. Right? Like when we defined our ID token, right? Did that just match the string ID?
Good.
I mean, okay, yes, it could. But does it just, if and only if, strictly match the string ID? No, right? And that was the whole point of tokenization, is so we could abstract all these strings and say, hey, I know there's an infinite number of identifiers you could write, but I will treat all of them, if they look this way, if they match this regular expression, I will treat them as the abstract token ID, right? And that way, for syntax purposes, I can make sure that when you're doing addition, you have an ID, a plus operator, and an ID, right? That you always have that you never have an ID plus semicolon, right? Because that's an invalid syntax. So that's why here we're dealing with tokens, right? We'll get to the next thing we're going to cover is, okay, we can build this tree, right, using this parser, but what does that tree mean? Which then you kind of have to go back to what are those IDs, what are the actual values of those IDs? But at this stage of the game, we only want to talk about abstract tokens. Now let's talk about some tricky cases that can arise when we're when we want to write a parser. And technology is just not my day today. Third time's a charm. There we go. The buttons work. Yay. Okay. Success. Okay. Let's consider think about something like this. Right, so can we do first sets of pretty much everything here?
It's gonna be
Right, so let's,
that.
let's start, what's the first set of A? A epsilon, B epsilon, right? First set of D, D epsilon, first set of E, E epsilon. So the first set of S?
A, B, D, E,
A, B, C, D, E, F, G.
D, E, F,
Was it?
Epsilon. A, B, C, D, E, F, epsilon.
A, B, C. So why is it C?
Because there's
Right, so
epsilon.
both A and B have epsilons in their first sets, which means we add the next one, which is C, to the first set of S. And then we add D, D, E, and F. Right?
Oh yeah, no epsilon.
Right, so no epsilon, because there is not epsilon in any of the rules here in all of their first sets. Right? Cool. Okay. Does this work? Yes, I think it works. Okay, we just want to, let's focus on writing the parse S function. Right? So, at first, what's the first thing I do?
Get to it.
Right? We call our lexer, we get a token. So do I check if it's an A, and then I'll know that it's this rule?
Check if it's an A, B, or a C.
Yeah, so I want to check, what am I checking? What did my rules say?
If it's in the first of that,
Right, this entire thing, right? This is alpha. We have a rule S goes to alpha. So we want to say, is it in the first set of A, B, C? Right, so what's the first set of A, B, C?
A, B, and C.
Right. Is there an epsilon in there?
yes. No, there is not.
Nope, because the C here, right?
Yep.
So yeah, so now I say, okay, if T type is equal to A, or T type is equal to B, or T type is equal to C, then what am I going to do? So do I call,
Parse A, parse B.
Determine whether you're not at C specifically, right? Because you don't know if you call unget token, if you look at all three of them.
so if I look at all,
Yeah, you call get token first, then parse A, parse B. And then C.
so the first question is, do I call unget token or not?
Yes,
Yes.
Yes, why?
because your first thing in there is a non-terminal.
Right, the first thing in here is a non-terminal. So, at this point, I don't know if this A came from this A, this B came from this B, or this C came from this little c yet, right? I don't really care, but I know that the first thing is a big A, right? And I know that that's not the token that that's a non-terminal. So I didn't generate that A or that B or that C at this point, right? So I call parse A.
I don't understand that.
Which part of that?
How do you know it's big A?
It has to be because of this rule, right? I'm using this first set to say, okay, in this first set, it's either T-type, must be either A, B, or C. Looking one character ahead, that's why I can choose it's S goes to A, B, C over S goes to D, E, F. Right? If it was in the first set of D, E, F, then I'd have to choose this other rule. So the first set helps me, the matching on the first set of the rule says, okay, I know it has to be this rule, So if it came, but I don't know that it actually came from this rule yet, right? I've only looked one character ahead. This rule could define a string that's 100,000 characters long, right? Or 1,000 tokens long. But I know that the first thing better be, like if I'm drawing my tree, right? I'm S, I know which of my children it should be. So now I need to say, okay, is the leftmost child, could it be an A? Right? And that's why I call parse A. So parse A is going to go, it's going to recursively build its own tree. It's going to return. If it returns, then we know we parsed an A successfully. So then what do we parse? Parse B. Right? Which would be trying to build this. And then if this happens correctly, it's going to build its own tree. It's going to return. And then what do I do? What do I want the next child to be?
C.
Little c. So do I call parse little c?
No, you get token. If it's not a C, it's sometimes.
Yeah. Right. So then what am I checking?
That token's not a C.
Then what?
Syntax, I guess.
Right? So now if I get here, I know I've properly created, so now after this, I know I've created this part of the tree, and so I've successfully parsed an A, I've successfully parsed a B, and I've successfully parsed a C. So now I know that this string did come from this grammar, right? S produced this, whatever my input string is. And so the kind of part of the point here is we don't have to special case this issue of, okay, we have a C here, but there's epsilons in A or B, so I could check if it's a C, that means it must have gone to here. We don't have to worry about that, because A and B will deal with the case that they went to epsilon, right? All we know is that after A and B return, we better have a C still to parse, otherwise something went wrong. Questions on this example? So what if I had changed it like this? How would that change right here?
It would just go AC. Or there would be a parse B.
And then inside of it, if block
Yeah, so the first thing actually that would change, but that's fine because we didn't pre-calculate it right, is that first set here would change.
Yeah.
Right, the first set of this is only AC. Right, there's no B because there's no epsilon, and the first set is little c. But how does this change?
You get rid of parse B.
Get rid of parse B.
Move it, actually.
I'm not going to do that, but I will rewrite it somewhere else.
Right.
Where should I rewrite
So
it?
keep that, all that stuff. Then after that, then you do another get token. And then if that,
After this
Yeah.
if clause here?
Mhm.
Here?
Yeah. Or not, get rid of that bracket, rid of it. There you go.
There.
Wouldn't you need to get token first?
Do I?
Yeah, because you got your token, that was a C, so you limited that. Then you need to get the next token to see if it's a B.
Do I have to do that though? Do I have any choice here about what this token is going to be?
I guess that could be handled with parse B.
Yeah, right. Parse B is going to make sure that its token is correct and that it's properly parsing a B. Yeah. So in this case, the tree we're generating, right, is S. We've had S goes to A generates something. Then we check, hey, we better make sure that that next thing is a C, right, which is what this check does. And then we say, okay, whatever's after that is a B, right? We have absolutely no choice about what this next symbol is. And then if it successfully returns, then we know we have, right, we've successfully parsed that string. What may I also want to check with S? We're going to talk about it. But at the end here, right? So I do this. Let's say I have everything properly. I've checked it, there's no syntax error in any of those other strings. What then do I need to check? Does this mean that it's a good string? Yeah.
You want to check for end of file,
Want to check for end of file? Why?
because if there's extra stuff, then you also have a problem. When you're expecting it to end, it ought to.
Right, so if we look at this grammar, right, if I have the string, we'll keep it as it is here. If I have the string ACB ABC, right, so we can have S goes to A, which goes to little a, right, which matches here. We have S goes to C, which matches here. We have S goes to big B, which goes to little b here. But there's still extra stuff, but I've parsed all of S. There's no possible way I could get these more, right? So this string is not in this grammar, so we want to make sure we check. Okay, we'll do one more check at the end here. So do we have to do this in everything?
Just
for the start.
the starting.
Right, just the starting non-terminal. Right?
Which is the starting non-terminal?
Traditionally S. I mean, that's the way we've been, right? So S has been the starting non-terminal. If it's not specified, S is the starting non-terminal.
Which you want to check for if it's not.
Yes.
in the file. And then
Could be a different token.
Hmm?
It could be a different token.
Right, exactly. If it's not end of file, like we know it, if it's to be correct, it has to be an end of file after S. So we parse all of S's. This makes sure that we actually have a tree that looks like this structure and that there's nothing after the input string here. Questions on this? Yeah.
So, again, when do you do this check for, well, checking if it's not in the file? Do you just run this after after the last token and what you're parsing?
You would do this after all of the rules for checking all the rules for S. So you'd say, okay, check the first set of this rule. Right? S goes to the first set of this rule. If it is, then you parse all those. Otherwise, if it's in the first set of this rule, then you parse that rule. Otherwise, it's the syntax error. And then after all of that, right, if you've successfully made it there, you correctly parse the whole tree, then you want to make sure there's nothing more after. Cool. All right. Look at us. Semantics. Now we get on to semantics. Text analysis in the dust. So what is semantics? So what have we done so far? What was lexical? What is lexers? What is lexical analysis? What are they doing for us?
token generation.
What was it?
Token generation.
Yeah, they're turning, right? So they're turning bytes into tokens, right? Because like we just talked about today, right? We don't care that IDs can be, that you can specify, an infinite number of things for an ID. All we care about is something at an abstract level of an ID. So then what did syntax analysis help us define from these? So syntax analysis, right, turns these bytes, turns them into a sequence of tokens. And what is syntax analysis helpful for?
Is it a valid program?
Yeah, does it, so not necessarily, not quite a valid program yet, but is this a valid sequence of tokens, right? Did this sequence of tokens, is it possible that it came from this grammar, right? Does the grammar that we have generate this sequence of tokens? What is kind of the data structure we want to think about from syntax analysis that we're creating? The tree, the parse tree, right? That's the way we want to think about these things. Is thinking about them in the parse tree. So, think about a language like, oh, I didn't bring the book. All right. Think about a language like C. Right? There's a grammar that specifies, a context-free grammar that specifies what a C program looks like. So is every possible string, every possible sequence of tokens that conforms to that grammar, is it a valid C program? Can you run every program that the grammar generates? No, why no?
It's perfectly possible to produce a program that's syntactically correct that won't work. If you've ever gotten a segmentation fault, this is what you know.
Has nobody done that before? Right? You compile a program, it maybe compiles fine. So it's syntax checks, right? So it doesn't say you're missing a semicolon, it doesn't say you have mismatched parentheses, right? It looks syntactically valid, but it's meaningless to actually try to execute, right? Because you're accessing memory, or the compiler is also really good about saving you from a lot of other errors, right? If it was just syntax, right? Like what happens if you try to use a variable that's never been declared in C or C++? That's an error, right? It actually won't even compile, but it's syntactically correct, right? There's nothing wrong with your syntax. And so semantics, that's where it gets into the semantics. Semantics means is about what does that parse tree mean? And how do we know what parts of that, like what parse trees are valid or make sense in our language, right? So up until now, we've been doing some kind of mechanical, in some sense, or turning bytes into tokens, sequence of tokens, and then turning that sequence of tokens into a tree. Now we get into some kind of deeper, how do we design languages, and how do we talk about the design of a language? Like can I just give you a context-free grammar and you can program it in my language? That'd be kind of awesome. Right, so how did you learn how to program in Java or C or C++?
Simple examples.
Examples?
Building off of knowledge.
What was that?
Trial and error.
Trial and error? Guided trial and error though, right? You weren't just randomly typing things in to see, right? You had this search space, but you kind of knew what was valid, so you tried different things to see if they would work.
The whole monkeys writing Shakespeare.
Yeah. I'm not going to call you all random monkeys, but so how do we do that? So what properties? So if we want to define our language semantics, right? What are we trying to get out of language semantics? Why is this important? Who is it important for? Do we care?
Ourselves.
Ourselves? Like our personal selves, like self-growth? Maybe. Why do you care about the semantics of Java or C or C++?
You want it to make sense.
If you want it to make sense, why?
So it works.
So it works. What works?
The program.
Yes, because you want to program in that language, right? You want to write a program in that language, and so when you say it works, what does that mean? What does it mean that it works?
What you type in gives you the expected output.
Yes, right? So that the machine is going to do what you expect it to do, right? That's the basis of programming, right? We're trying to convince this stupid, incredibly fast machine to do something for us, right? And all we have is our silly little English style, like that's the way we want to do it in, but it wants ones and zeros, right? And so how can we make sure that what we envision, how we want our program to work, how can we make sure that the computer understands the same thing, right? Because at the end of the day, if it doesn't do it, you're wrong, right? Doesn't matter how much, you can't just will the computer to do what you want it to do, as much as we all wish we could. Maybe someday. I know, then you could hook your brain up to the computer. I'd be worried about going the other way though.
Right. Rogue AIs and whatnot.
Exactly. So what do you want when you're trying to study, when you're trying to understand a programming language? What do you want from the semantics? Yeah.
It needs to be very clear for both the programmer to understand what the language will support, but also for the computer to make sense of what the programmer is trying to tell it.
Yeah, so there's two different, it's not only you developing the program, it's also the compiler writer, right? They want to make sure that when you, the programmer, write something, if it's in the semantics, it better do that thing, right, for you. So it needs to be precise, right? It needs to be precise. Okay, this is what happens. What other features are useful? What other things? Human readable, yes, right? You want to be able to understand it, right, as a person. You know, it's not, machines aren't reading most of the time semantic documentation, right? It's humans. What else? What about predictability? Is that important?
Yeah.
Yeah? You want to make sure that the program you wrote today is going to work a week from now or on Tuesdays and Wednesdays, not on Fridays, right?
How difficult would it be to write a program like that?
There's a language called intercal. It's a joke language, but you have to say please enough times. Otherwise it won't. It'll complain that you didn't say please enough. It's actually really cool. Oh, spelling is important. So what if the semantics, I don't know, what if they're incomplete? Which is bad spelling. What if they're incomplete? Is that useful? If it doesn't specify all possible semantics, right? If it doesn't say how something should happen, and you write a program that takes advantage of that, what happens? What does the machine do?
We don't know what it will do.
Exactly. Yeah, we can't predict it. It's about predictability. It's about preciseness. It's about conveying our thoughts and our algorithms to the machine. Okay. So when we get back, I want you to think about, on Monday, how we can specify language semantics. So think about the ways you've learned programming languages, and you learned, what does it mean when I call a function? When I add two numbers together? When I concatenate strings? How did I learn that, and what are the different ways of doing so?
Good enough, right?
No.
I don't understand the unget token.
What don't you understand about it?